It is a pleasure to see you all here. Especially there are a few people that I really appreciate coming here, and certainly they have come a long way to support this particular lecture. Especially I would like to thank Bob Connor that he came here today instead of going to the pub and probably watching the Manchester United game that is currently on the go. And please keep me informed on the score, since I support Manchester United too. Obviously this is my inaugural lecture. It's certainly something very special for me, and I hope you're going to enjoy it as much as possible. The electronic architectures and organizing vehicle subsystems is something that is it is very hot topic, and I'll explain you why. In terms of the contents, I will give you something to think of as we go forward within the lecture in the very beginning, and then I'm going to talk a little bit about the commercial vehicle evolution, some major systems that exist currently in terms of the X-by-wire systems, some vehicle electronics architectures in terms of how we see it in the Vetronics Research Center, and then I will conclude the lecture on this tone. Okay. This particular extract from the New Scientist, it actually says quite a lot of things. It talks about a 911 call that came in 2010, and there was a person calling 911 to saying that something has gone wrong with his car. In particular, it was the acceleration. So it started accelerating and went out of control and so on and so forth. It was a Toyota Lexus. And it was one, as we are going to see in a bit, it was one of the first cars, if you want, that started to having this X-by-wire systems, the drive-by-wire systems, and so on and so forth. The problem with that was that something happened, and they still cannot find exactly who was at fault, if it was the actual vehicle, the electronics, was it mechanical, or was it a human error. So as we go through the rest of the presentation, hopefully we'll start thinking about the problems and issues that they come with this type of systems. So from the commercial evolution point of view, Carl Benz introduced in 1885 the very first normal vehicle that we know as of today. And at the time there were only about 1,000 petrol cars in the world. Later on, obviously this has changed dramatically, and we are talking about in 2009 something like 1 billion vehicles existing in the world, and an annual sales something like 50 million. And obviously with the new commercial powers with India and China, these figures probably they increase quite dramatically and in exponential type of numbers. At the same time, the road safety, because of a number of different legislations and so on and so forth, this has relatively gone better throughout the years, but there are still an estimated 1.2 million people are killed in road crashes. And projections say that most probably this is going to increase with as I said, with the new countries, India and China, obtaining so many new vehicles. Many systems, in particular when they are new, very innovative, they take many years to actually come through. And Ferdinand Porsche in 1901 developed the very first hybrid electric vehicle. And this became available eventually in 1997 through the Toyota Prius. And since then, a number of different sales, obviously, they came up, and the cumulative numbers, we're talking about something like 2.3 million vehicles in the entire world. But you can see how it was spread. The very first one that came in the beginning of the century, and towards the end of the century, then it was actually became a proper production vehicle. Saying that, there are other technologies being pushed across the motor industry, like the vehicle data communication buses, so networking within the vehicle. And the very first one was a Cadillac with General Motors in 1980. And then following on, the first drive-by-wire system with the BMW 7 Series that came in 1988. Since then, other experimental things, they came obviously into the production. And in 2003, Toyota Prius came and provided this automatic parallel parking. A very interesting and very innovative way of obviously parking, but there are certain issues with that, which I will explain a little bit later on. At the same time, a lot of legislation came in place, and one of the things that the United States introduced, it was the diagnostics. So it meant that every single vehicle that was coming out of the factory should have some kind of onboard diagnostics, so that they can understand if something was going wrong and anything that was supposed to make the availability of the vehicle much quicker and much better for the user. And to add on top of that, the last few years, as we all know, and it hurts us a lot, certainly in our pockets, is the price of the petrol. So all this, they come together, and obviously they create a number of different issues that one has to address. From the very beginning, the electrical systems within the cars, they were very basic. So we're talking about turning on lights, turning on the indicators, and so on and so forth. And as the years they were passing, the cars obviously they were getting better. They wanted more electrical things to go on, more electronic things to go on, and came to a point where just basically too much to go into the car. Chaos in terms of cabling and putting the manufacturing processes together. So that's how the field bus technology came about. So literally the networking, it's what we call the vehicle electronics, if you want, within the vehicle. So a number of buses, communication buses, they came into play, and these have reduced dramatically the amount of wiring that is required within the vehicle to operate, to have different functionalities. This gave this X-by-wire capability within the commercial industry. So in essence, what is X-by-wire, which evolved, if you want, with the buses and so on and so forth? Really what it does, it replaces traditional mechanical control systems with electronic control systems. And these electronic control systems, they in essence are electromechanical systems where you've got the sensors and the actuators, and accordingly, basically they replace any mechanical part that is possible. For example, the steering column. A steering column is certainly something very crucial for the car. It's literally behind the steering wheel. And you can imagine the steering column coming out, and you've got literally a piece of wire, obviously with the electronics around it to support what we call the steer-by-wire. The advantages of using X-by-wire, some of them they are obvious, some of them they are not obvious. The obvious thing is that it reduces dramatically the number of parts that they move within the vehicle. Obviously, when you turn the steering wheel, there are a number of different mechanical bits that they have to turn as you turn the steering wheel. A steer-by-wire, for example, that would remove all these different parts of the mechanical side, if you want, that they have to twist and move, and you literally have just a few wires and a few control, if you want, electronic control units that they are able to do the same job. This means that also the weight reduces quite a lot from the vehicle point of view. And at the same time, you can use all the electronics to provide what we call the diagnostics. So anything that could go wrong within the vehicle, you could detect it, either address it very quickly, or potentially be able to have what we call the prognostics, so be able to address whatever potentially will go either bad or break, even from the mechanical point of view, so that you can certainly protect the vehicle and obviously anything that has to do with the maintenance of the vehicle. And of course, having all that, reducing the weight, being able to have the diagnostics and understand how the vehicle operates and the functionality and so on and so forth, also reduces the emissions. So basically you've got a better working engine and obviously the fuel efficiency accordingly. All is good, but technology always provides the good stuff, but there are always the negative stuff, and one has to be careful how you can address these certain issues that they are appearing with the technology. Certainly the X-by-wire systems, they are quite complex. If you start adding more and more things, we saw the vehicle earlier that had obviously the buses on it. But nowadays we are talking about every vehicle, a normal vehicle that we see on the road, to have something like 30 to 100 individual electronic control units. And when you have to integrate all these and the services that these units they provide in terms of the data and information and so on and so forth, it's quite complex. It is not an easy thing. At the same time, someone has to consider also the safety aspects of all that. Replacing the steering column, which is entirely mechanical, with an Italian electronic version, the electronic control units and the drive-by-wire, or even have some autonomous tasks like the parallel parking, or some quite drastic things that they probably will come in the future, like change automatically lane in the motorway. These are quite safety demanding things that one has to consider and design. Then on the other side you got the user. So the user will have to understand, accept this type of new technology, these innovations, and be able to drive in probably in an entirely new way. Things like steer-by-wire, you would normally wouldn't have the feel of the road exactly as it is. So there are new systems that they come back with what we call the force feedback. Like that you can more or less understand what is happening on the road. So when you drive and you go over a bump, and you can feel, if you want, the steering wheel actually move according to the environment that the vehicle moves. And of course all this, certainly in the beginning, when you've got the new technologies they cost quite a bit. So the cost it's quite high in the beginning until there is the acceptance and obviously the mass production and so on and so forth, where it reduces the cost quite dramatically. And finally, which is again related to the user, it's as soon as you start playing with networks, it means that the network is available for either malicious users to go in and attack your network, and obviously the privacy. So again, there is a number of things one should take into account considering these new technologies. Very top level, if you want, the different vehicle systems that one should look at is grossly, if you want, the mechanical, the electrical, electronics, and the man-machine interface. The mechanical structures, it is very obvious. You've got obviously the chassis of the vehicle, and you've got the engine. The payload structure is primarily what the vehicle is about. So it could be a van, it could be a truck, it could be a passenger vehicle, and so on and so forth. And then you come to the electrical electronics, which is the more obviously the things that we are talking about today, really, when we're talking about the power architectures or the distribution of the electrical architecture. The different utilities, the lights, the sensors that are used, some special features, the things like the automatic parallel parking and so on and so forth, and of course the diagnostics. Very important is the man-machine interface. The man-machine interface is anything that has to do with the driver and how it operates the vehicle. And one of the things that has been looked at quite dramatically, if you want, from a number of different companies, is how you can integrate a lot of the services of the mobile phones, be it Ericsson, be it Nokia, be it from whatever, to actually put it on your vehicle and have access to absolutely every service that you want. And again, it's a lot of the human factors that they have to play there. And even now we know that we are not allowed to actually use the mobile phones within the vehicle. And now we want to use the mobile phones to do many more services within the vehicle. And this presents also the security issues and so on and so forth. So there is a lot that can be quite dangerous unless one takes care, basically, in particular on the design side. So the way we do it at the Vetronics Research Center is to look at the architectures and see how we can make complex things as simple as possible. And this is the definition that IEEE uses for architectures, and more or less as we adapt it in the electronic architectures of a vehicle. So it's the structure of components and interrelationships and the principles and guidelines governing the design and evolution over time. I think that more or less says everything in that. At the same time, because it's a very complex system, you have to consider that there is a lot of mechanical, electrical, all the interfaces. There is a lot of safety, embedded design, software design, and so on and so forth. So there are very unique expertise that one has to put together so that we can address all the different issues related to the entire vehicle system. And I want to think that in the Vetronics Research Center we have actually achieved to have all this expertise in one place. And this is the uniqueness, basically, of what we are doing. I'm not going to go into the very details on the technical side of what I'll present to you from now on, because I don't expect you to understand absolutely everything. Sometimes I don't understand them myself. So I've got my boys in my group to tell me how it is. So this one, it's a typical, what we call the V-cycle, typical V-cycle in terms of developing a system. It's literally just a fraction of that. Normally what you do is you develop from the left-hand side and you test from the right-hand side. And what you do is you look at the user requirements in terms of the driver, for example, what you need the driver to do and the functionality of the system. Like that, you can meet the functional requirements. You can put the functional requirements to meet the user requirements, and then obviously the technical requirements so that you can meet all the above. And finally, you come into the architecture bit where you develop the architecture so that you can satisfy all the rest of the different requirements. And of course, from the other side, as you develop, you also test. Now, the important thing that we are doing here is when we do this development, we try to look at the risk of the systems. So if you have an early risk management within your development of the system, then you can probably mitigate against the different faults or anything that can come up. We also follow certain standards and guidelines, and these are very, very important, so that we can use them as the enablers, if you want, of the whole process and the whole essence of the system, the vehicle systems. Defining these standards, then we can also start looking at partitioning the whole design in terms of the architecture. And look at the service-oriented, capability-oriented type of approach from the systems engineering. And when we start looking at and understanding how the architecture could be in this modularity, in this service-oriented type of approach, then we start looking at the technologies and see how we can use these technologies and fit them accordingly to meet the requirements of the architecture. What we also did is we said, okay, if we look at the service-oriented architectures, the capability-oriented services, then what we can do is we can classify accordingly. And then the architecture can follow this type of approach. So what we did is we put them as 3 different categories. And the safety critical category is obviously the most important one. And the things that they go there is primarily things like drive-by-wire, anything that has to do with autonomy or automation. Then we got the deterministic, which is a little bit more flexible, if you want, from the safety critical class of services. And primarily because, as we'll see later on, is when you have a safety critical type of application, network, service, then you need the appropriate certification so that the design can actually demonstrate that it is actually foolproof. So in the deterministic side of things, we're looking at the utilities, diagnostics type of services, and the non-deterministic, then we're looking at other utilities such as data collection, infotainment, you would call it, diagnostics, and so on and so forth. This is a typical, what we call a generic architecture, and what we see here is if you want a collection of buses, a connection of networks, so that provides, if you want, the core of the vehicle. That's where all the communication is done. We've got the different subsystems. It could be sensors, it could be the drive-by-wire, air conditioning, and so on and so forth, and utilities. We've got the diagnostics, potentially training systems. So basically, when you go into the trying to learn how to drive, then you could use this type of systems, again electronically controlled. Obviously the power systems that they can provide the juice of the network so that it can operate. And obviously the drivers and potentially what you would have, why not even the passengers being able to contribute towards the whole vehicle. And of course, all of this, they have to be integrated through standard interfaces, what we call them the gateways, so that they can provide this inter-networking capability. And this is a loosely coupled type of networking, so that you can have what we call the logical connection and also the physical connection later on when you start applying the actual technologies, the network technologies within the vehicle. Now all the systems, because they are all interconnected, they have to be what we call the dependable systems. We have to consider the dependability of the systems. And this is just a typical example of a safety critical bus with a steer-by-wire capability. And the attributes, when we look at dependability, is basically, and very, very importantly, is the availability of the system, reliability, the safety, the confidentiality, integrity, and maintainability. Again, I'm not going to go into the details of this because there are, each word of this, it's a full section for research. The thing that puts everything together, it's what we call the safety cases. Every new system, every vehicle normally has to have a safety case. The safety case is the thing that actually says that this product, this vehicle is actually safe to go on the road. It's a certification that says, yes, we are there. And what you do is within these safety cases, and our approach is to, and our research, if you want, is on the modularity of that, so that you can have the flexibility for the future upgrades and so on and so forth, is to look at obviously the entire system, and then each of the subsystems that goes underneath this whole vehicle system is to have the different the different safety case, if you want, that they provide the different modules of the safety case that overall can come and build a very solid safety case or a solid system, if you want, at the end. So we're looking at the different solutions to the different goals within the whole system and the strategy within the architecture of the safety case. What is important here to understand is that when you have a vehicle system like that, one of the assumptions that, and very, very important assumption, which will probably force the conclusion a little bit towards the end when I'll conclude the lecture, is that this assumption is the human. So every vehicle, obviously nowadays, has got a human. So the human has to be trained appropriately so that you can drive the vehicle. So imagine when you're talking about an entirely new way of driving, drive-by-wire, entirely different concept. So every single person that actually buys a new car that is drive-by-wire enabled has to understand how it could operate, how the training would be to actually educate the person that is behind the wheel, that is not going to do anything stupid, certainly not to kill himself and certainly not to kill others. So it is very, very important. One of the important things that we put together is how, okay, we can put all these ideas together, and the different subsystems is how to test them. So we put together quite a comprehensive testbed, a very unique testbed, which, and again, I'm not going to go into the details, this is very, very top level. And we have added within the architecture safety critical networks, obviously what you see here on the left and the right, and this is the FlexRay, and this is a TTP, time trigger protocol. We have put a deterministic network in the middle, a Milcan, And we've got also different non-deterministic, but still real-time networks as the backbones up here. The uniqueness of this testbed is, obviously in terms of the flexibility and the capabilities that it has, is this little stimulus that is in the beginning. We call it the spider. And it can test the entire network. It doesn't matter the configuration of the network, and it can do it what we call non-intrusively. So it means that you can have in the front end everything working and as a normal operating capability of the whole network. And this one will actually do all the testing, just fire faults on the network and collect all the data and make sure that what we do is the appropriate way to do it. And this is in actual fact the reality of the testbed. It's been developed through a number of years. That was an exhibition that we did, excuse me, last year. And what we'll see in a bit, it's a different way to present this type of testing, if you want, this network. And we used a little Buggy, which I'm going to show you in a bit how it operates. The architecture of the Buggy, it actually follows the architecture of our testbed, more or less mirroring the capabilities, but obviously the testbed is much more comprehensive. It's got a lot more on it. And what we can see, it's we've got again the subsystems in terms of the X-by-wire, so the safety critical subsystem, and we can see the red bus here that represents, if you want, the safety criticality of the system. We've got the utilities, the crew station, and situation awareness, basically it's video. And these are the gateways, which are very important in terms of the interconnection of the different subsystems within the vehicle, and also anything that has to do outside the vehicle. So remote diagnostics and so on and so forth. So the red cable, if you want, the bus, it's the safety critical bus. The yellow one is the deterministic bus, and the green one is in actual fact the non-deterministic bus. What we'll see as an example in terms of the safety critical system on the Buggy is the drive-by-wire. And in essence, what we have, we have three different subsystems within one drive-by-wire system, and this is the throttle by wire. It means that you can press, you can accelerate, and we're going to see that through or electrical electronic means. You can brake by wire, so exactly brake without having mechanical means. It's all electrical electronic. And of course, the most important one and the most difficult to achieve is the steer by wire, which in essence, as you can see here, there's no steering column. You've got a motor there that actually detects how you steer the vehicle, and then an actuator that actually turns the actual wheels. When we decided to put this particular demonstrator together, I had one of our supporters and very good friend. He said, "Oh, you need to make electronics as attractive as possible, because when you show them around, there's no attractiveness. It's just a board and a piece of software. It doesn't do anything." So he said, "Try to do something. Think something to put together so that you can not only prove your point, but at the same time make it attractive for other people and relate to it." So what we did is we went and we got a little Buggy. It was all mechanical, nothing fancy to see, and we started building it from nothing. We are no mechanical engineers. We are just purely electrical electronic engineers, and we managed to put this thing together. It's a very unique piece of equipment. It's fully integrated. Obviously, the driver is fully integrated too. You can see it here. And what was remarkable is we put together within 3 months, and it worked first time. I mean, that was a very big achievement. And when I'm saying it worked first time, it didn't obviously work perfectly, but it did work. And this was actually the first time that we videoed as evidence. That was the very first time that we took it out on the road. The transition from this one, it goes a bit slow, and particularly because we want to see the transition from the reverse to forward gears and see how this was reacting. And it did work very well. It's got the capabilities of this little buggy are quite amazing. You can literally use with the integration the steering wheel that we see here to actually do anything you want. It doesn't need to do only steering the vehicle. You can steer anything. What we see here is the sensor for the accelerator. Oh, sorry. Yes, it was the accelerator, wasn't it? Yes, it was the accelerator. And this is the brake-by-wire. So the sensor here and the actuator on the other side. And the steer-by-wire, which is obviously the most difficult bit to do. So we see the steering wheel with the motor and this one detecting where it should turn. And this is the actuator to actually turn the wheels. The user interface, like I say, everything is electronic. So you can start the engine, you can use the different lights, turn them on, turn them off, all with this user interface. And the good thing with that is, obviously, this is just purely the user interface. It's nothing fancy. But for us, it was more to be able to see how the entire network, the whole integration actually works. And to give you an understanding what I mean, it's, for example, in a normal car, when you press the brakes, you need to make sure, obviously, that the brakes, they are pressed, and this is the #1 priority. But at the same time, you need to show the brake lights, the one that is behind you, that you are actually pressing the brakes. And there are two entirely different subsystems. So you got the safety critical subsystem that actually deals with the brake-by-wire, and in a utility subsystem, which is just literally deterministic, that deals with the actual lights. The other good thing is with this type of work and approach is not only that we are proving the concepts, but we are doing it very cost effectively. So we did it in much less cost, and we proved the whole thing. And at the same time, we had great fun. You can see some of my guys here. I told you he was a bad driver. It was good fun. It was very good fun to develop the whole thing. One of the things we left this one as an example. That wasn't because Ian, the driver, was actually a bad driver, but a very obvious thing that we detected there, it's you can have your safety critical system, everything fine, go through the entire process, no problem, give you no problems whatsoever. However, when you look at the power, if the power is not enough within the vehicle, and it doesn't matter how much you certified, it will not work. And that was exactly the problem there. So the batteries were running flat, and as soon as it went down the battery to a certain level, then the buggy was doing, well, it had its own mind after that. Now the other incredible thing that we are achieving within this concept of electronic architecture, the subsystems and how you put together, it's how fast you can actually improve your system. And one way of that we tried to prove that we can do something like that very quickly, we selected the most difficult bit of the whole X-by-wire system, and we selected the steer-by-wire, and we said, okay, let's see how we can improve that in terms of having multi-steering inputs. So instead of having just a single steering wheel, then use a joystick as an additional way to drive the vehicle. And at the same time, you can use the same thing and the same concept to actually steer the vehicle remotely. So that's exactly what we did. And we see here again one of my guys giving a demonstration. You can see him steering the vehicle with just a normal steering wheel, and then seamlessly just transfer from just simple steering with the wheel to go to a joystick. So we can see him here driving with a joystick. And again, the amazing thing is this particular addition to it. It took us probably 3 months to get the whole thing going, do the safety analysis and so on and so forth. and 3 weeks to actually integrate the whole system within the vehicle. Okay, and to conclude the lecture, so we need to see the X-by-wires obviously as an entirely new technology. It is very much feasible, and certainly it's probably yes, it's a very complex thing, but we can actually achieve it if you plan it appropriately, and you can design the whole system and provide this risk management from the very beginning, and so on and so forth. You can comply with all the safety legislation, the security. All these are fine. Probably the cost also as a through life cost, and you can manage it accordingly, and probably can be again as a normal vehicle can be bought, is no problem. But when we're talking about commercial vehicles and you've got the human in the loop, as we say, to be able to train all the number of people to actually drive these X-by-wire vehicles, it's probably going to be very, very difficult. And one of the critical things is, if something goes wrong, whose fault is it? Is it the actual vehicle's fault? Is it the mechanical fault, the electronic fault, or is it the human fault? And obviously the acceptance that has to go with it. And probably the insurances will have a big saying on that too. So really, all these concept cars that they are out there, and there was, I think, also a few weeks ago, there was a big show with new concept cars. They are fantastic and everything. I think that it's probably going to be quite difficult to come to a stage where you're going to think, yes, we've got a kit car on the road. I think it's going to be very, very difficult. However, there are certain areas within the vehicle industry that is certainly very, very applicable, and is going to be extremely useful. And these areas, obviously, they are certainly the military, emergency services, anything that has to do with obviously the police and the fire brigades and ambulances and so on and so forth. So, and this, I certainly believe that these are literally around the corner, whereas the commercial vehicles will probably have to wait a little bit longer. And that's it. Thank you.